Bom, boa tarde a todos. Estão me ouvindo? Ok, então vou apresentar o professor Federico em inglês e a gente vai dar início ao segundo dia de conferências, ok? So our first speaker of today is Professor Federico Holik, who will talk about foundations of Non-Kolmogorovian
probability theory.
Theory of probability theory. Yeah, I'm sorry. Professor Federico is a fellow of CONICET and La Plata National University, and his main areas of research are quantum information theory and quantum logics. So, thank you for coming, Professor.
Thanks to you. First of all, I wish to thank the organizers of this conference for giving me the opportunity to give this talk. I think that this conference is very important, and the fact that many experts from different disciplines are gathered here to discuss about these topics is a pioneering thing in Latin American region, so I hope this conference repeats again in the future. So I will try to speak about quantum probability and what will be the meaning of that, and the differences with classical probability, and how can we speak about a generalized probabilistic formalism. The story will start with the work of Hilbert. Hilbert's sixth problem. I will try to tell the idea behind it. So during the International Congress of Mathematicians held in Paris in 1900, David Hilbert presented a list of 23 problems of mathematics which, in his opinion, should occupy the efforts of mathematicians in the century to come. I'm going to quote Hilbert in his paper. You can see the complete list of problems here, but we are going to refer only to the sixth problem. He says, the investigations on the foundations of geometry suggest the problem to treat in the same manner, by means of axioms, those physical sciences in which mathematics plays an important part. In the first rank are the theory of probabilities and mechanics. This is very curious because he's situating probability in the physics side. He's putting them together. So because he's dealing in this problem with the axiomatization of physical theories. And then he continues and says, as to the axioms of the theory of probability, it seems to me desirable that their logical investigation should be accompanied by a rigorous and satisfactory development of the method of mean values in mathematical physics, and in particular in the kinetic theory of gases. So Hilbert himself dedicated big efforts to solve his sixth problem. And the officially accepted solution for probability came in 1933 with Kolmogorov's axioms, which are based on measure theory. That's one of the most important axiomatizations. Of course, it is not the only one, but it was one of the first rigorous approaches. But Hilbert's contributions were influenced also in the development of relativity theory and in the development of quantum mechanics. Indeed, quantum mechanics acquired its rigorous axiomatic formulation after a series of papers by Hilbert, von Neumann, Nordheim, and Wigner. And it is agreement when we say that the definitive form of the quantum formalism was accomplished in the book of von Neumann in 1932. But it is important to remark that the book of Kolmogorov was published in 1933. But the first reasonable axiomatization of quantum probabilities appeared already in the year 27 by a paper of Hilbert, von Neumann, and Nordheim, and there was an independent work of Jordan. And von Neumann's masterpiece was published in 1932. So these different formalisms were developed together at the same time. But of course, the Kolmogorov's approach was more famous because perhaps it was more difficult to understand quantum phenomena by that time. And of course, the vast majority of applications can be relied on Kolmogorov's axioms. And another important historical fact is that Hilbert was von Neumann's advisor. So it is the same guy who posed the problem in the year 1900, and he afterwards searched for concrete solutions to the problem that he posed. So first, in order to understand quantum probabilities, let us try to understand what is meant by a classical probability. But of course, most of you know about this, but I'm trying to point out some important facts about this that will be used in the rest of the talk. So suppose that we throw a coin, and if I do a run of the experiment, I get two possible outcomes, heads or tails, x and y, and a probability measure will be two numbers, px and py, between 0 and 1, that add up to unity. And for example, if the coin is unbiased, we will have px equal to 1/2 equal to py. It will be a 50% coin. But in a more general situation, when you take a coin like this, you don't know if it is a biased coin or not. It could be a 70-30 coin and so on. So for this concrete coin, there are many, and indeed infinitely many, probabilistic states in which I could prepare the coin. The preparation involves the whole thing, the procedure of throwing the coin, and all the variables involved. And then I get the result, and then I can perform the statistics and measure whether this is a fair coin or not, and to try to determine the state by looking at the frequencies. But then, a probabilistic state of the coin will be given by the pair of numbers, px and py, and you can decompose a vector like this in this way, always. Px product 1, 0 plus 1 minus px because of this equation, 0, 1. And this will define, by varying the value of px, all possible states of the coin. So in one of the extremes, you have the state 1, 0. This state means that each time I throw the coin, I will obtain the outcome heads with probability 1. All the times that I throw it, I get 1. In the other extreme, you have 0, 1, which means that I obtain tails always. And just in between them, you have 1/2, 1/2, the first coin. But each point in this line segment will represent a possible probabilistic state of a physical system that has two possible outcomes. Now, the first observation that I want to make is that this line segment is a geometrical object. So in the rest of the talk, we will speak about the connection between probability theory and geometry. And there's another interesting connection, which is the connection with algebra. The possible outcomes of this coin are x and y. And then their conjunction as sets is the empty set, and the disjunction is the set xy. This is very simple, but it is a very important algebraic structure, and it is known as the Boolean algebra of two elements. So this is the algebraic side, and this is the geometric side. Now let us see what happens with an experiment with three outcomes. I have x, y, and z, and then probabilities px, py, pz, between 0 and 1, they add up to 1. And then when I start to look all possible probabilistic states of this system, a quick study shows that all possible states can be considered as points in a triangle. And then for this model, we have a geometrical representation of all possible probabilistic states as points of a very concrete geometrical object, which is a triangle. Now, the algebra of events associated to these three outcomes set is given by x, y, and z, and then you can form, for example, the disjunction between x and y. You can make x or y. If you want to bet on that, this will be represented by this set, and so on. X or zeta, this set, and so on. And for example, if this event happens, if this outcome actually happens, this one will also happen. So this will be an order set, because this guy will be lesser or equal than this one, and so on. And for example, you can make the conjunction. You can bet on this proposition and this proposition. And the conjunction will be just the intersection between sets. I am trying to tell this without doing mathematics, but there is a very concrete algebraic structure behind this, which is that of a Boolean algebra. That will be a very important object for us. In a Boolean algebra, we have lines that connect the different events that could occur as outcomes of an experiment, and these events are ordered, partially ordered, and we can make intersections, conjunctions, or disjunctions. For example, negations. The negation, the proposition X does not occur will be represented by this proposition here, which is either Y or either zeta occur. So there is an algebraic structure going on, and there is a geometry associated to these three outcomes probabilistic model. Just in case you don't remember, the set on the left is convex, and the set on the right, it is not. It is not because if I take the line showing these 2 points, A and B, some points of the line lie outside of the set. So for every classical probabilistic model, the set of all possible states of the system will be a convex set. And that is a very precise mathematical object. And we will see that it is much more precise. Because convex sets, for example, have faces. For example, F1, this vertex, and this vertex will be faces of the convex set. But also this line here, and this line here. All these objects can be defined in a technical way. I will not do that. I will try to put it all with images and words. But this can be formalized very clearly. And every convex set has a collection of faces. We also add by completitude the empty set and the whole set. And it turns out that if you look at the algebraic structure of the propositions associated to the outcomes of the experiments, and if you look at the algebraic structure that can be defined between faces, they are isomorphic. So the first message is that there is a connection between the algebra and the geometric representation of a probabilistic model. How is this? How do these lines, for example, this one is behind this one because they are included. This one is included in this one. And this one are included in this, and this is the least upper bound. And for example, if you want to get this one, you compute the greatest lower bound between these guys here. So all of this can be formalized, and you get an isomorphism between the algebraic representation and the geometric representation. This will be very important because I will tell the end of the story right now, so it is clear. In quantum mechanics, we will also have an isomorphism between the faces of the convex set and the lattice of propositions. But the algebra will not be a Boolean algebra, so the algebraic structure will be different to this one. And the geometry will not be a triangle or a line or what I'm going to tell right now. The set of states or probabilistic measures associated to a quantum system forms a very concrete mathematical or geometrical object which is different in shape from those of the models that come from classical probability theory.